Okay, Rodrigo, it's all yours.
All right, thank you. Well, thank you guys for having me. So yeah, so I'm Rodrigo Sarlo. I'm a assistant professor at Virginia Tech Civil Engineering. That would be a lecturer in England. We were just discussing that. So my title, my talk is entitled "Improving SHM Multi-Structure Adaptability via Reduce a Priori Information." I'll get to what that means in a second, but it's really just an opportunity to highlight some of the research coming out of my group, particularly for two of my doctoral students, Hessam Soleimani and Alan Smith. So we focus essentially on built environment monitoring and evaluation. We do a lot of vibration, large-scale vibration work. So this is just some of the more recent ideas that we're developing. I think they have a lot of synergy with some of the stuff that the DRG group is working on, particularly from what I've seen in population-based structural health monitoring at recent IMAX. So hopefully this is really an opportunity for me to highlight some of our work and explore some ideas and potential collaborations with this group and hopefully create a long-term connection here. So let me start by introducing or defining what I mean by multi-structure adaptability in SHM. So there's been an interest in the SHM community recently about designing SHM systems for that are adaptable and deployable in a variety of structures or families of structures. So that could be as extreme as, you know, a bridge and a building, or it could be certainly a set of similar structures. But the way you generally go about this is for each structure, you would design a data acquisition system, extract and organize and structure the data or models associated with the data, such as finite element models, extract informative features on that data, and then design a damage detection system on those features. Now, if you want to transfer information from one structure to the other, you run into some bottlenecks. In terms of data, you have to see if the models are of compatible structure with each other. Does data in one structure mean the same in another? For features, are the features physically relevant from one to the other? And in terms of damage detection, all the way down the line, are the parameters that you've chosen, such as thresholds and detection windows, going to result in consistent performance from one structure to the other? Now, the population-based structural health monitoring that I've seen from the DRG group, which I'm a big fan of, takes a particular approach where you try to essentially resolve some of these bottlenecks by defining standardized frameworks for organizing data, rules for mapping similarity between structures, rules for transferring knowledge between structures. What we've done is slightly, or what I'm going to talk about today is slightly complementary to that, where we actually try to start with no a priori information about the structure we'll be dealing with and design a framework that's essentially general, structure agnostic, if you will, and then feed in the data at the end and allow the framework to essentially resolve some of the structure-specific nuances. So to give you some examples of what I mean by a priori information, essentially it's offline information that's somehow injected into the system in some way or another. So one example could be an assumed structural geometry, which is used for defining and updating an FEM finite element model, or simply just defining the structure of the data that you're dealing with, sensor locations, things like that. Another example might be previously collected damage examples or labels, which are used for feature extraction and training a machine learning algorithm. It could be things like long-term baseline data. So a lot of times you'll collect a year's worth of data to normalize your features for environmental conditions. Or it could be user-defined detection parameters, so thresholds and things like that that are used to tune the algorithm's damage sensitivity. So I'm not necessarily saying these things are bad. They're actually very useful in a lot of cases, especially if you're looking at specific structures for specific damage cases. But they do limit our ability to kind of adapt or extrapolate to to different domains, different structures. And so these essentially result in some specific challenges, which I'll focus on today. So one challenge kind of stemming from this assumed structural geometry is that in the end, you end up having differences between the as-built and as-planned behavior. So if your models are not reflective of the as-built conditions, or maybe the as-built evolution of a structure, you can have some discrepancies about what you expect and what actually is happening. And then the last three examples kind of add up together to create case-dependent or structure-specific results that are then hard to essentially transfer from one domain to another. So I'll talk more specifically about these as we go on. So the way I'm organizing this is I'll talk about essentially two projects, part one and part two. The first project is a framework we've developed for going from reality capture techniques to as-built models. And that addresses that as-built challenge that I mentioned. And then part two would be on a framework we're working on for unsupervised SHM. That is essentially that idea of going with as little a priori information as we can. And that's to address this kind of case-dependent, structure-specific challenge. So I'll start with part one, which is based on reality capture. So I'll start by elaborating on the as-built challenge through just kind of a simple preliminary study that we did. So we built a experimental frame in our lab, which you see on the left there. And then we used LiDAR to extract a point cloud of this frame and then extract the precise structural geometry of the structural members as well as sensor locations. And then we built a fine element model based on that geometry. And so when you do that and you compute the first mode of that structure, you see that it's has a diagonal behavior to it, which is not what happens when you actually use the as designed fine element model, assuming perfect geometries, right? That's more of what you would expect in an ideal case where you have a very linear mode and obviously a symmetric mode in the other direction. What's interesting is if we actually do experimental or actually operational model analysis on this structure to extract that first mode shape, it looks a lot more like the as-built FEM, which is kind of reassuring. So what this is stemming from is essentially small imperfections in the way that the structure was built and fabricated. So in the end, the structure had a little bit of a twist to it, just based on small imperfections. It's hardly perceptible, but even just accounting for that, we get a lot closer to the as-built behavior. You can imagine if we just go with an as-planned model and try to update the material properties based on the observed behavior, we can end up with some very funky results because we're not actually taking into account geometric deviations. So that's just an example of that problem. And so our objective in general is to use reality capture techniques to things like LiDAR and photogrammetry to get all the way to an as-built digital model. And that could be a fine element model, it could be a building information model. And there are a few steps in that path. The first two steps are segmenting structural elements from the overall point cloud that may include a lot of stuff we're not interested in, and then doing 3D geometry extraction, so extracting basically functions that define how those elements are organized. And then there's two other steps. Material identification would actually give you an idea of the material properties of the structure, and also some extraction of engineering properties like boundary conditions and joint stiffnesses. So our method so far focuses on the first two. The second two is stuff that we haven't quite gotten to yet. So what's been done so far, there's actually an emerging community, I would say, in the area of as-built modeling. One of the kind of more visible groups is one led by Yannis Brilakis in Cambridge, actually. They focused a lot on building information modeling or just a semantic classification of structural elements. So here you see an example for a concrete bridge. A lot of their techniques focus on how components are organized in space. They focus on large blocky structures, basically planar features in the point cloud, and they work all in the 3D space. So that tends to work really well for concrete structures like this one, but we were more interested in steel structures and slightly more complex geometries. So we took a slightly different approach, which I think also is much more scalable, as we'll see, than some of these other methods. So our approach essentially, in a nutshell, is we start with the original point cloud of the structure. We slice it into images. This allows us to use image processing techniques rather than point cloud processing techniques, which are much further developed. And then we use these techniques to extract centroids for structural cross sections of interest, and then we basically map back out the structure based on those centroids. Okay, and this is based on a recent paper that we published in Computer-Aided Civil and Infrastructure Engineering. So let's start with that first stage. So we essentially get a full point cloud. This is a point cloud of an actual building. You can see that it's the structural elements are exposed, but there's a lot of clutter. So there's lighting, there's shelving, there's a lot of equipment around. So it's certainly not an ideal case. And so the first step is to really slice this into images. And so we do that by essentially slicing along the 3 principal axes of the structure. And so this is an example for the Z direction. We slice it and we get essentially slivers of the point cloud. We usually do about 1,000 slices per direction, roughly speaking. And so then we have to flatten these slices into images, and we do that by essentially pixelizing or voxelizing the point cloud point. So anything that falls within a certain pixel just gets, that pixel gets colored in, and then everything else is blank. So you can see that there's obviously, you have to think about resolution here. You know, more pixels per unit distance will give you higher resolution. So there's a balance there in how you do that. Then once we have the stack of images, this is really where I think that the real benefit of this method comes in that we can use image processing approaches to filter the images so that we get rid of most of the noise. These are pretty noisy images to begin with. And then once we've filtered out some of the irrelevant information and have more clear cross sections, we can use convolution to try to, basically as a template matching operation, to try to identify the centroids of these cross sections of interest. And then we map them back into 3D space. So the filtering is where, you know, the power of this technique comes in. We start with an intensity threshold that's able to, just based on the reflectivity of certain elements, we can isolate structural components. So you can see how there was a wall here, a non-structural wall that got eliminated. Can you guys see my cursor, by the way? Hopefully you can. Maybe you can't.
No, we can't.
Let me go to a pointer. Can you see the pointer?
Yes, we can see it now.
Okay, excellent. So yeah, there's a wall here that gets eliminated by the threshold. Then we do some moving averages to smooth out, get a better resolution image. We binarize the image, and then we still are left with somewhat of a sparse point cloud here. So what we do is we use morphological operators to essentially close a lot of the gaps and get to a more reasonable cross section. So once we have that, we can apply convolution. We select a relevant kernel for the type of structural element that we're trying to detect, in this case, an I-beam cross section. And when we do a 2D convolution with the original image, we're left with, you can see that most of the irrelevant information is essentially removed, and we're left with high correlation values at the points where we had the I-beams. And so the highest point there corresponds to the centroid, so we can essentially threshold that out, and we get our centroids of the relevant cross-section. So mapping that back out to 3D space, we see that the original point cloud, which is essentially this whole image you're seeing here, just super dense, millions and millions of points, is reduced to a very sparse centroidal point cloud. It's still pretty noisy, but we can use a technique called region growing to actually identify strong linear segments within this point cloud, and that defines our centroidal axes for the elements that we're interested in. So, going from a pretty noisy point cloud, this was sliced in the z direction, so this is aimed at identifying columns. We can see that there's a lot of noise, but there's clear linear regions, so we can extract that using this process. Sometimes there are spurious lines, but those can be removed with just simple geometrical rules, right? You don't expect a column to be horizontal. And the final piece of this is that we look at then elements that we obtain by slicing in different directions, and we say that the places where these are closest should be a connection, right? So they don't exactly overlap because there's some offset, but the closest distance between them, the two, is defined as a linking element, and that allows us later to update connection stiffnesses and boundary conditions and so on. So here's an example for a pretty clean building. This was an airplane hangar. And so you can see that we're able to extract the columns, girders, even purlins with a high degree of fidelity here. So we have a very high fidelity structural skeleton of this building. And going back to this idea of as built versus as planned, we actually compared this extracted geometry in green with an as planned model, basically a handmade model from planned drawings, which is in purple. And you can see that there are some pretty interesting discrepancies, particularly in the columns here. In the planned case, the engineer assumed that this would just simply be a vertical column, right, just for simplicity. But in fact, the columns, because they were prismatic or non-prismatic, the actual center line is diagonal. And then there's also some discrepancies in terms of how the purlins line up, and this could be due either to actual deviations in the way the structure was built, or just simplifying assumptions made when the engineer was making the model. And as we saw before, even slight simplifying assumptions can have some interesting implications for the dynamic behavior of the structure. So they're not trivial differences. Here's another example of the cluttered building I showed at the beginning. So doing the centroidal extraction, we get something that's pretty noisy. We clean it up, and then we do the region growing. And so we get, again, a high fidelity structural skeleton of that system. And here is from the inside. You can see how the center lines line up pretty well with, just kind of visually, with the structural elements, despite the fact that there is a lot of clutter around here, lighting and shelving and so on. So just from a qualitative perspective, this is working well. And so just to demonstrate that this can be used to create fine element models, we took this information, we added some manual definitions for material and engineering properties, and we're able to define basically a preliminary fine element model. Obviously, this will require some refining to be reflective of the structure, but this is just to show that this information is compatible with fine element models. And to get back to this idea of multi-structure or multi-domain adaptability, we collaborated with the University of New Mexico to apply this same technique to rebar cage inspection. So this is an inspector using a handheld laser scanner to scan a rebar cage before it gets poured. The result is on the right. So again, a pretty noisy point cloud here. And same technique, just by changing the convolution kernel here to a circle, we're able to extract the centroidal positions of the rebar cage and essentially recreate the rebar spacing, which can be used to give an inspection rating to this particular rebar cage if it conforms to the code. And it can also be used to document the precise rebar layout before the concrete is poured, which can then be imported into a finite element model to be, again, a more precise representation of what the actual structure is. So to conclude this first part, some of the big takeaways from this work have been that using this 2D approach versus 3D helps to reduce the complexity of the problem while enabling us to leverage some powerful image processing techniques. In combination with that, the convolution strategy allows us to define basically flexibility in the definition of cross sections, and this essentially allows us to be very flexible in terms of how or which structures we can apply this to. So we saw that we did it for various buildings with very small changes, and then we even applied it to a rebar cage. So this is the beginnings, I think, of a digital twin framework, and also a way for monitoring, essentially having a model that evolves with the structure over time. So by automating this process, we can actually track as built conditions over time and stop relying on as planned assumptions. Okay, so that's part one. It's 10:24. I can pause here if there are any questions. I think this is a good pausing time.
Hi, so
Okay.
yeah, absolutely fascinating work. I was just wondering, in the filtering image, when you sort of remove a lot of the noise, do you go in and double check that the geometry that you get as a result is close to the beams that have been scanned? It just sort of seems there's quite like a lot of parameters potentially in the thresholding and the dilation and erosion steps.
Mm-hmm.
I was just wondering how you verify the resulting geometry.
Mm-hmm. Yeah, so that's a really good question. We had a lot of discussion about exactly how you would define the ground truth in this case, just because you can see that what we're trying to do is we're trying to get away from the plan drawing. So using the plan drawings as ground truth wasn't a good idea, or it was not what we wanted to do. So essentially what we ended up doing is we looked at the variability in terms of, after we extracted the line, how much did the points around that line vary, and we used that as a kind of surrogate for how accurate it was. And then we just kind of also just visually verified. We went through the laser scan and we made sure that the original point cloud and just like you saw in the video, that the extracted center lines were at least qualitatively doing what we expected them to do. But it's actually really challenging to define kind of a precise accuracy metric in this case.
Thanks.
Mm-hmm.
Hi, Rodrigo.
Yes.
It's really nice. I was wondering, I imagine it's a computational restriction, but if you thought about trying to do a 3D convolution of like an element of an I-beam through the point cloud, rather than just the 2D approach, because it seems like if you did that, you could track the convolution line along the beam, possibly. Maybe I'm completely wrong.
No, I think I see what you're saying. So like, you mean do a 3D element and convolve that in 3D?
Yeah. So some nominal thickness of I-beam element, and then convolve that in 3D with the point cloud. I didn't know if you tried this already, or if there was some reason it wouldn't work.
No, we didn't try. I think in essence, some of the 3D there are some machine learning based techniques that I think essentially do learn some sort of 3D convolution that they do on the point cloud to do this. So I think it's certainly possible. I think the advantage of the 2D is that we can actually do things like the morphological operators, which is a lot harder to define in 3D. But I think you could certainly define the problem in 3D. We just didn't. We thought that, well, let's start with 2D. That might be simpler.
Yeah, for sure, for sure.
Yeah.
Cool. Thanks a lot.
Mm-hmm. All right. So I guess I'll move on. I can certainly leave some time for questions at the end as well. Just thought I'd take a breath here. So great questions. Thank you. So let's move on to part 2. So this is more SHM oriented, but again, under this theme of kind of creating systems that are less dependent on kind of a priori information. So the challenge we're trying to address here is what I'm calling the case dependency challenge. So going back to some of the a priori examples that I gave, I'll give some limitations that arise out of this. So for example, with label damages, one limitation is, and I think a relatively obvious one, is that you can't deal with unseen damages, right? So naturally, so there's been kind of the push in SHM to move towards unsupervised learning techniques, right, to avoid this problem, because obviously we can't have examples of all the damages we expect to see, or sometimes there's damages we don't even expect. But even within the unsupervised techniques, a lot of them rely on certain physical features. So these might be, at a simple case, modal frequencies or modal parameters. There may be spectral energy quantiles, or there may be more complicated unsupervised dimensionality reduction techniques, such as an autoencoder or something of that nature. But all these, what they do is they're essentially pretty severe dimensionality reduction, which, if we don't know what we're looking for, can mean that perhaps we're discarding important dimensions. So our proposed solution to that is essentially sticking to high dimensional features, developing frameworks that deal with essentially as close to the raw data as possible, and go from there. And then the final a priori example that creates a challenge is this idea of long-term historical data. Obviously, this is good if your environmental conditions are stationary or consistent over time, but just taking the example of climate change is probably not safe to assume that historical conditions are necessarily reflective of future conditions. And so if conditions are changing, this is kind of limits our ability, or even if conditions are changing between structures, right, not necessarily over time. And so our proposed solution for that is just short-term online training, just limiting the training to online and relying less on historical data. So let's start with the features. So the features we chose for this, by the way, this is based on a study we recently, actually we're working on publishing. It's on preprint right now, if you're interested in the finer details. But the high dimensional feature we settled on for this study is essentially the FFT of each channel of data. So we take the FFT magnitude of each sensor channel, we concatenate them all, we create a high dimensional feature. Now, obviously, we're discarding phase information here, but we felt that was easier to deal with, but this is still pretty close to the raw data. And the nice thing about the FFT that it's pretty, basically you can run it on any kind of data, so it's not really specific to any type of structure. It's really fast to compute, so it's pretty generic, pretty simple to implement. And so the challenge that arises with the high dimensional features is essentially techniques that can actually deal with such high dimensional data and produce reasonable results. So I'll get to that in a moment. The unsupervised online learning framework that we came up with relies essentially on no prior information. So the system goes online and then the detection essentially starts. The way we set this up is that we have a stream of sensor data coming in. So this is for one sensor. Obviously, we have various sensors. That data stream gets split into segments. of about 1,000 points, order of magnitude. And then those segments get grouped into a training window, which is about 100, order of magnitude of 100 segments for a training window. The FFT feature gets calculated on these segments. We train a one-class classifier. What that means is essentially a classifier that tells us whether a new segment is from the training population or from outside of it. Once we have that classifier, we define a detection window, which is essentially a group of segments that will try to decide whether this is a novelty or not. So we extract the features for those segments, and we use some sort of novelty score to essentially aggregate the data from the different segments to decide whether there's overall a novelty or not. And this detection window can actually vary, and a lot of methods actually do vary that detection window. And so we play around with values like 10, 20, 40 for this detection window. Obviously, the longer it is, the more the less noisy your detection will be, but sensitivity could go down. At any rate, so once we detect a novelty, we have essentially two options. We can just continue monitoring for other novelties. This would essentially constitute a static baseline approach, right? Or we can just train a new classifier and reset the process. So define a new training window, retrain the classifier, and this would help us identify changes from the detected novelty. And this is what we call the dynamic baseline approach. One big challenge that comes out of this framework is that our training window is actually quite small. So if we're sampling at 100 hertz, which is pretty normal, that comes out to a training window of about 16 seconds for these numbers. 16 minutes for these numbers. So that's not a lot of data to deal with, and especially if we're dealing with high dimensional features. So we need a way to actually address that. And so what we came up with is actually leveraging this idea of generative adversarial networks, or GANs. So if you're not familiar with GANs, the way they work is essentially it's a competitive game between two deep neural networks, a generator and a discriminator. The generator takes random noise as input, usually of a low dimension, and then converts that to a fake feature, which in this case would be our FFT features that I mentioned. So that's a high dimensional feature there. And that gets fed in, or many examples of these fake features get fed in along with the training set to a discriminator whose job it is to essentially distinguish fake from real. So based on the discriminator's performance and some sort of back propagation, the system is trained so that in the end, if you do this well, you have a generator that's really good at generating features that resemble the training set, and you have a discriminator that essentially has a random chance of flagging those features as real or fake. But as a result of this kind of adversarial training, the discriminator is much more robust than if it would just have been trained on the training set alone, which is nice because we have a relatively small training set. So this helps us kind of make a more robust discriminator. On top of that, we actually have two neural networks that we can leverage for our purposes. So the discriminator ends up being our one-class classifier if you treat real as a no novelty case, essentially baseline case, and fake as a novelty case. So when it classifies something as fake, you can say essentially, okay, that's a novelty, that's outside of our training class. And then the generator is essentially a data set amplifier. We can have an endless pool of baseline-like features that we can use to robustly test the statistical behavior of the discriminator. So in this case, we're going to use it to test the false alarm rate of the discriminator and see essentially what is the distribution of scores that the discriminator gives for stuff from supposedly the training set, and see what decisions we can make on that. So the way we do that is we use a reliability-based approach. So our objective here is to make at least the threshold that we choose. So the discriminator outputs a score, basically from 0 to some number. the higher the score, the more confident it is that this is a novelty. So we want to set a threshold for that score that defines basically a robust measure of a novelty. And the way we do that is we generate a bunch of samples from the generator, and we look at how the novelty score is essentially distributed. And so here you see the histogram of scores. And so the objective is to choose a threshold that guarantees us a low probability of false alarm for any choice of detection window. So the detection window, everything, all that information, all the user choices go into how the score is determined. So the score is a reflection of all the choices that the user has made. And so when we choose the threshold, when we tune the threshold, it's taking all that into account. And so essentially, we limit the area past the threshold to a very small number, and that means that our false alarm region is very small. So it's a lot of stuff to think about, but so this is just an overview of kind of how everything fits together. So we have our data stream, we split it into segments, we define our training window, and so we extract the features, and then from the features, we train a GAN, right? And that GAN gives us both a generator and a discriminator, two neural networks. The generator is used to generate samples, and actually along with the discriminator, tunes the thresholds, just like you saw. And then we run the detection, where we extract the features and use both the tuned thresholds and the discriminator to try to identify novelty based on whatever choice of detection window we establish. And if we identify novelty, then we basically reset the process. We train a new GAN on a new baseline case and then continue. Okay. So the nice thing about it is that we can also define scores essentially however we like, as long as it's a function of the GAN output, which is what SGAN is here. This is the discriminator output. So we can define, for example, 20th percentiles, which are essentially the lower bound of the scores that we're seeing out of the detection window, or we can define higher percentiles. There's a lot of nuance here that I just don't have time to get into, but essentially the detector that we decided upon was an ensemble of two detectors, one detector which is fairly conservative, so uses kind of a lower bound of the scores, and a detector which was a combination of a more aggressive GAN detector, basically lower threshold, and another set of features which I didn't talk about, but is essentially a reduced version of the FFT. So we actually took the area under different percentiles of the FFT and used that as a low dimensional feature and just trained another classifier on that. And the idea behind that is just to make it a little more stable in terms of the noisiness of the detector. But essentially, we have two detectors. If either detector detects a novelty, then we consider it a novelty overall. Okay. The exact details don't matter too much. What we're actually going for here is that regardless of how you define that detector, that the performance should be relatively stable regardless of the detection windows and other parameters that you choose. And so to do that, and also demonstrate how adaptable this framework is, we tested on a couple of SHM benchmarks. So the first one was the yellow frame, which you see here is a miniature building frame, and the damage is simulated simply by removing some of the bracing elements around the structure. And so these are the results here. And there's a lot to read here, but the way you should read it is that start at the bottom here. This is the raw data. The red lines represent the initiation of damage, essentially when a frame configuration was removed. And so when you have a damage initiation, then you move up. And this shows the GAN score, basically the novelty score from the GAN discriminator. And you see that it peaks every time there's a damage initiation. And there are two thresholds. The first one is the more aggressive one, and then the top one is the more conservative one. If the score exceeds the conservative one, that's our first detector that's immediately flagged as a damage. So as you see, these cases, these were all pretty obvious novelties. Sometimes the novelty is not so obvious. That's when we use the more aggressive threshold. So if that's exceeded, then we also check the lower dimensional feature score up here. And if both of those are exceeded, then we flag a damage. Okay. And so you can see that basically all the damage cases were identified. And we had one case of a false alarm over here, which essentially it detected damage where there wasn't any. So obviously you can define a detector that could be better or worse here, but the important thing is that it's consistent. So in this case, we used 25 segments to derive these scores, right? To basically, we aggregated 25 segments to obtain a score. In the next case, we actually used 40 segments. So you'd expect, as you're using more segments, the information gets less noisy. You see that it kind of smooths out. But at the same time, you would expect, if you stay at the same threshold, you would expect that sensitivity to go down. But actually, the thresholds adjust down because we see less variation in the way that the score is distributed. And so essentially, we get pretty similar performance. We get all damages are detected, plus we get, actually in this case, 2 false positives very close to each other. So that's the kind of thing that we're looking for, is essentially stable performance across different user selections. We did the same thing with the Z24 bridge. Again, key here is that we apply this to different structures, not just one, right? Because we want to make the case that this is not structure specific. Applying it to the Z24 bridge, we got different performance for that detector. We actually didn't get any false alarms, but we did get a few false negatives. So for example, in this case right here, we see that there was no damage detected when there in fact was damage. And so we had, I think, 5 or 6 cases of that in this. So that's not ideal, but actually the ones that were missed were simply increased severities in damage. So in the case of the first one, this appeared being lowered from, it was at 80 centimeters, it's lowered to 95. But any new damage types, essentially when the label changes, they were all detected. So that's at least positive. We were able to detect changes in damage type, just not necessarily in severity every time. All right. So that's for a detection window of 10. When we go to a detection window of 25, again, the data gets smoother, but the thresholds adjust, and we actually get the same level of detection. So everything that was detected before is detected again. So there's actually no change in the overall novelty between the two cases, which is what we're going for. So stable performance. And just to wrap it up, we compared this as well with other SHM studies. For the yellow frame, we used a study by Hahang G. Alameda. And in this case, this was a dynamic baseline approach, but using kind of low dimensional features. I think he was using energy quantiles of the spectrum for each case. So what are we looking for here? So he also changed the detection window length, just as we did. And if you notice, for our study, basically our true alarm ratio is pretty good. It's 100%. But the important thing that it's consistent. Same thing with the false alarm ratio. It's essentially kind of oscillating around 0.15%, but it's relatively consistent. For his study, you can see there's a trade-off. As you go higher in the detection threshold, with the detection window, sorry, you actually get reduced sensitivity you get less true alarms, right? So reduced sensitivity to damage. As you go down, you get higher false alarm ratio, right? So, so increased sensitivity essentially comes with a higher rate of false alarms, which is what we were trying to avoid and stabilize for. For the Z24 bridge, we couldn't find a study that actually did this dynamic baseline case, only something that did the static baseline approach. So we implemented that as well. We modified our algorithm so that it just did the training once and then just identified basically damage, no damage. And we see that we identify about 96% of damage cases across the board. So independent of the detection window, we get pretty much stable performance there. Undamaged cases, 100%. Their performance was about the same, right? Ours was slightly better, but I think not a strong claim that it was extremely better, but we can make the claim that you see that our performance is relatively stable, whereas as they increase the window size here, the performance starts to decrease, or at least the damage case identification gets less sensitive. The opposite is true for undamaged cases, but again, there's a trade-off here for their studies, which we kind of avoided. What's also kind of notable is that they used the 1-year baseline data to actually train this classifier, whereas we trained online on the first 5 minutes or so of data, which is kind of interesting. Obviously, the nature of the Z24 bridge damage data kind of was conducive to this because it was captured over a very short period of time. So the environmental conditions weren't a huge deal. We haven't yet adapted the framework to deal with severely changing environmental conditions, but still, I think showing that this works this well based on a very small amount of training data is supportive of the fact that the high dimensional features in combination with the GAN is an effective technique. And so just to conclude, right, going off of that, the high dimensional features give us an ability to kind of avoid limitations from dimensionality reduction, and seems to be a powerful classifier if you combine it with the GANs. And specifically, we're using recurrent neural networks to do the classification. The GANs themselves help us make up for limited data, especially in high dimensions, and we can leverage both discriminators and generators in their own way. And in particular, the generators are leveraged in a reliability approach, which helps us stabilize the false alarm rate and performance of the algorithm independent of user selection or user choices, which is nice because that's one less bit of a priori information that you have to worry about, right? You can select it, but the performance will be relatively stable. So coming back full circle now, you know, if our goal is multi-structure adaptability in SHM, hopefully I've convinced you that there's a couple of elements of this work that fit into this. In terms of data structure, data organization, the SBIL modeling could be an interesting tool, not only to make sure that our models are compatible with the way things are built, but also perhaps to quantify slight differences between structures in a family of structures, which may have the same plans, but may have slightly different as-built configurations. And so we can quantify differences even down to that level, and do that as the structure evolves over time. At the feature level, we've seen that these high-dimensional, very general, very generic features are actually quite useful because they're not domain-specific. And when combined with online training, they allow us basically to get rid of any sort of a priori or more, a priori information that we may need to do the classification. And we can deal with relatively limited data. And then finally, at the damage detection level, the reliability analysis shows that we can at least stabilize the performance of these SHM algorithms, regardless of the precise damage detection parameters that were selected, by essentially running kind of simultaneous offline tests to try to tune the threshold with artificial data. So, so that's it. If you would like to contact us, here's my email. We also have a website if you want to check out some of our other projects. And it looks like I'm relatively on time, so hopefully we can have maybe around 8-10 minutes of questions on the second part or the first part. So it looks like No, no problem. So it looks like Keith raised his hand.
Yeah. Thanks, Rodrigo. That was really interesting. Just a couple of remarks, really.
Yeah.
The dynamic baseline approach you have there shares some similarities with something Tim Rogers, who's probably been quiet and modest, developed based on Dirichlet processes, where you essentially start off with very little a priori information and then investigate alarms as they come along, and either continue to discover novelty or to accumulate labels for a classifier. So it might be nice if you had a chat with Tim about that. The other remark is I wasn't really, I didn't quite get what you said about Z24. Z24 has got some fairly marked environmental variations associated with it, quite special ones in a way. And there's quite a lot of studies attempting to deal with that in the context of novelty detection. So if you want to get pointed in the direction of one or two references, just give us a shout and we can do that.
Yeah, I think that's a good point. I think I didn't express that idea very well. So at least the data set that we dealt with, yeah, and I remember reading quite a bit of literature on trying to understand the variation in modal frequencies for Z24 with respect to conditions. But the data sets that we had essentially were a long-term data set for about a year, which was essentially a healthy baseline set, which did see a lot of variation. But then the damage detection data set that we used was actually a lot of damages introduced in a very short span of time. So over that span of time, there wasn't what we observed to be a drastic change in environmental conditions. So we felt that in a way that was somewhat advantageous to us, because
it will have been potentially if you started running your dynamic baseline just before the damage started, because it will just run into the damage. But if you started at the beginning of the year with the healthy baseline data, there are some really interesting fluctuations caused by cold temperatures that flag novelty fairly comprehensively, actually. So it's an interesting data set.
Yeah, and in fact, as we were working on this, I thought about the next step would actually be to run this on the long-term data set and see how well it deals with these fluctuations. So that's something that we're working on, and something that we're kind of interested in seeing if the dynamic baseline approach can kind of capture recurring baselines, if you will. So when the bridge returns to a certain condition, that we understand that it was there previously, and try to use that as information for understanding environmental fluctuations versus damage, which isn't necessarily returning to the original state.
Yeah, it's all really interesting stuff. I think you want to talk to Tim about this, maybe.
Certainly, we'll do.
Thanks for dropping me in it, Keith. But feel free to get in touch, Rodrigo, if you
You're
want.
welcome, mate. I know you're not busy. I know you're not busy.
Julian, I think you has raised his hand. Do you want to pop in?
Yeah, sure. I find the use of the GAN, that's a really cool approach, and yeah, it looks like you got some really good results from it. I was wondering, if the detection window doesn't have much of an effect, how do you sort of decide on an optimum? Are there other kind of factors that you consider when choosing that? Or, yeah.
So what we've gone for is essentially kind of eliminating the need to choose an optimum window. We know that there's several techniques out there to choosing an optimal window, so we haven't really delved very deep into that. But so far, I think what we were focusing on is, let's say you're not necessarily, you obviously need some sort of reference detection window length. You can't just go, down to 1 or, up to a crazy large number. But if you have some relative idea of where you should be operating, then fluctuations around that really won't impact too much. So we kind of tried to avoid the optimal detection question, but I think it would be possible to one, just implement previous approaches, or even maybe leverage the GAN to define an optimal window. We just haven't looked at that yet. I think that's a good point. Does that answer your question?
Yeah.
Okay, I think Shandy has a question.
Yeah, hi. Thanks, Rodrigo, for that. That was really nice work. I was just wondering about the dynamic way of doing it versus static way of doing it. So by retraining the GAN, do you not lose out information from sort of what you've learned before, or is that I'm quite new to GAN, so I don't really exactly understand how it works. So what's the benefit of sort of retraining every time you see novelty versus not retraining at all?
So Lizzie is saying that she can't hear you. I could hear you, so I'll repeat the question. So the question is what's the benefit to retraining the GAN in the baseline approach, or are you just losing information from doing that? So the way we see it, we're not losing information because we can still keep the old GAN. We just essentially train a new one. So we're essentially training a set of 1-class classifiers for each new baseline case that we see. So the benefit that we get from that is that we can detect changes in damage or changes in damage intensity from one stage to the other. We also potentially, like I was mentioning to Keith, if we are seeing fluctuating conditions, they may be flagged as a novelty, but if they return to normal, we can kind of go back to an old model that we trained and see, so we can basically come see if new conditions are the same as old conditions. Essentially, are they recurrent or are they completely new? Does that make sense? Okay, Julian, you have a question?
Yeah, that just sort of got me thinking in terms of like, could you then have a range of GANs potentially to try and cover more of the normal operating condition if you had GANs that were sort of trained during particular environmental conditions?
Yeah, so that's a very good question. It's one I've thought about, but one we haven't really tried to implement yet. But the GANs do raise some really interesting function, or provide some interesting functionality, right? You're drawing, there's some techniques with GANs where you can, so the random noise is what we call the latent space. And so you can actually move things around in the latent space. And so for example, for images, I think the best way to do it is through an example. So they're actually able to look at different images of people and look at where aged people are relative to young people in the latent space and the random noise from the GAN, and then move around, basically take a picture of a new person, move it slightly toward the old space of old people, and then actually artificially age the image. And so I'm curious to see if you can do something like that, but with environmental conditions. So if you capture GAN's models for different sets of environmental conditions, if you can kind of move them around and try to kind of see how they're related in the latent space and try to come up with a more basically a more continuous model for how things change. But that's all speculation at the moment. We haven't really looked into that.
Yeah, I mean, that'd be fascinating if you could actually sort of move that around and just get potentially even just like simulate what the model would be doing with unseen environmental conditions, right?
Yep, exactly. But so, or what would we? I think the way we're thinking about this in a way is not a continuous model, but essentially, yeah, these discrete scan snapshots of different conditions, and then the question becomes, what are, can you move from one to the other, and so on. But yeah, really, really interesting.
Thank you. I see that we have run over, so it's 3 minutes past 4 here in the UK. So I think we will finish here. Thank you for a really interesting presentation, Rodrigo. Very clear as well. I'm not a specialist in SHM at all, and it was very clear. So.
Well, yeah, I was actually worried about that. I kind of assumed some basic knowledge of SHM, so hopefully I'm glad to hear that it was clear.
No, it was really good. So I'll send the recording to everyone who, I'll send the recording to the Dynamics Research Group, and Rodrigo, I'll send it to yourself as well. So if you want to share it in your group, you can do so as well. And yeah,
Great.
well, thanks once again. And if you want, if you're happy to share your slides, you can send those to me and I'll distribute them in the group. It's up to you.
I will do that as well, and I'll probably reach out to a few of you, particularly Tim, and we can follow up on
Sounds great.
some topics. All right, thank you guys. That was fun.
Okay, thank you.